All right, so we're gonna continue what we were doing last time. So let me just briefly recall what we have learned about integration yesterday. Oh, yes, we don't have time to review. I checked the number of lectures that we have. We only have, counting today, 3 classes left in the semester, and we need them to cover the sections missing from chapter 7, so 7.3, 7.4, and 7.5. So the downside is we don't get to review. The upside is you're going to have 24 hours to do your exam, so it should be fine. So let's quickly review what we learned last time. So we learned about lower sums and upper sums. So recall from last time really quickly. What is it that we learned? Well, we define upper and lower sums for a partition. So if regular P is a partition of the interval AB, then we define the lower partition and the upper partition with respect to P as this. Where mk is the infimum of the function f of x over the x's in the interval xk minus 1 xk. And the partition P is a x0 less than x1 less than x2 less than xn, which is b. That's the standard notation we are using. And we also define the upper sum. It's very similar, only instead of using the infimum, we're using the supremum. Capital MK is the supremum of a function on that same intervals. Then we define the upper interval and the lower interval as the corresponding infimum and supremum. So then L of f, that's the lower interval. That's the largest of all of these guys for all partitions. And U of f, the smallest of all the upper sums. We also learn that in fact all of the lower sums are smaller than all of the upper sums, and that's important. We have a question here. N and look the same. Right. So right now the only answer here, I'll be careful about that, especially so they look on the screen. All right. And yeah, so we learned last time also that all of these L's are always smaller than all the U's. So the picture you should always have in mind is that there's a real line, and for any function, you have all the U's, all the L's on the are always smaller than the U's. So these are the U's, and these are the L's. And they're always like this. So that means that the supremum of the L's, and it's always smaller than the supremum. Well, this is one of your exercises in the homework to show that this is actually smaller than that one. But it kind of makes sense if you have two sets that are like this. It's intuitively clear, right? And then the point is that the function will be integrable, Riemann integrable, if these two are the same. So lastly, f is integrable if L of f equals U of f, in which case the integral of f is either of the two. whichever one you prefer. Okay, so that's a quick summary of what we did last time. Well, and we also had this theorem, which is going to be our workhorse, which says that a function is integrable. So let me put it here. So this is also theorem 7.2.8, which is called the integrability criterion. Says that f bounded on AB is integrable if and only if for every epsilon there exists some partition p epsilon such that the u minus the L of that partition is less than epsilon. All right, that's going to be, we will use this all the time to prove something is integrable. We're going to use it extensively. Okay, so let's now start with something new for today. So we announced this theorem and we'll continue. So this is theorem 7.2.9, and it says that a function that is continuous is integrable. So it says if f is continuous on the closed interval AB, then f is integrable on AB. Okay, let's prove this. Good. So what do we need? Well, we're going to use some of the things we know about continuity. In particular, this is continuous on a closed interval, right? And this is compact. So something that we know about continuous functions on compact sets is that they are in fact uniformly continuous, which is always stronger and a nicer property to have. So because AB is compact, right? It's closed and it's bounded, obviously, and F is continuous. It follows that F is uniformly continuous on AB. Okay, and why is that going to be good? Well, because then it allows us to say the following. It allows us to control how big the difference of the function is if two values are close to each other, right? So just to remind you what this means, it means E for every epsilon, there exists some delta such that if x and y are within delta of each other, then f of x minus xy are within epsilon of each other. And for reasons that you don't know right now, but the length of the interval, so from A to B, the length of A to B is going to appear somewhere along the way in my proof. So you don't see it right now, but I'm going to require this to be, so instead of doing it for epsilon, I'm going to do it for epsilon over B minus A. Okay, this is how I'm going to use it. Okay, you can use whatever epsilon you want, right? This is what it says. So that's how we're going to do it. So we're going to pick an arbitrary epsilon. Let epsilon greater than 0 be arbitrary. And use the line above for uniform continuity with epsilon over B minus A. Okay, so we're going to need that. And another thing we're going to need is the fact that continuous functions achieve their maximum and their minimum on a closed interval. That was our so-called extreme value theorem, all right? But I'll tell you when we use it. So we're gonna pick a partition. So let P be a partition of the closed interval AB, and I'm gonna pick one where the length of the intervals, so xk minus 1, I want them to be less than delta. And I can do that, right? Because all I need to do is, so let's recall again what we're doing. So we started with an epsilon. Using this epsilon, because of uniform continuity, we know there is some delta that makes this happen. Now pick that delta and then pick a partition where the length of the intervals is less than delta. And you can always do that. For example, you can pick the big interval a to b and divide it into n pieces, where 1 over n, and n equal pieces, where 1 over n, or the length of the interval over n, so each one of the little pieces is less than delta. So this can always be done. This shouldn't be surprising. And then now here comes the part that I was telling you. By the extreme value theorem, this happens. This guy, which is the supremum of the fx over the x's that are in xk minus 1 xk, it's actually achieved, right? By the extreme value theorem, the maximum and the minimum are achieved. So the supremum happens to be a maximum. So this is f of some number. And let me call it, what I'm calling it in my notes. So it's f of some ck, for some zk in the interval xk minus 1 xk. And the same thing for little m. So the infimum happens to be a minimum. The infimum, it happens to be a minimum because it's f of some value. In this case, I'm going to call it yk. And the same for some yk in xk minus 1 xk. Good. So now it's time for us to calculate so we're going to use our theorem before, the theorem that I referenced before. Let me put it up just momentarily. So we're going to use this theorem. We're going to use that something is integrable if and only if we can find a partition that makes this less than epsilon. So we have to calculate this. What is this? U minus L of the partition. So that's what we're going to do now. We're going to calculate U minus F, and let's do it. So what is U minus F? U of F of P epsilon minus L of F of P epsilon. The upper sum minus the lower sum. What is it? Well, it's going to be a sum from 1 to n of, if you put them together, is capital MK minus lowercase mk of xk minus xk minus 1. Correct? Didn't do anything here. Now here's where I'm going to do something. See, what is mk, capital MK minus little mk? Well, it is f of zk minus f of yk, correct? And this guy is the maximum and this guy is the minimum. So this is actually positive. This difference is positive. And because it's positive, it's the same as if I put absolute value like this, right? But also, more importantly, both the y and the z, both yk and zk, are in the interval xk minus 1 xk, right? They are both in this interval. So they are close to each other, right? Both the y and the z are close to each other. And what did we know about things that are closer than delta? Let's go back right here on top. And our initial assumption was that if two things are closer than delta, then their function is less than epsilon over b minus a. So that's what we're going to use here. So this is less than epsilon over b minus a because zk minus yk is less than delta, right? They are less than delta because we chose the intervals to be smaller than delta, right? So these two numbers belong to the same interval, and the length of the interval is less than delta. Therefore, the distance between them two is less than delta. And because they are less than delta, then their images are smaller than epsilon over v minus a. So that's awesome. So I can control this part over here, right? So this mk minus little mk now will be controlled this way, right? So then u of f p epsilon minus L of f p epsilon will be smaller than the sum from 1 to n epsilon over v minus a times xk minus 1. Now this is a constant, so I can take it out. And then all I have is xk minus 1. But if you realize, this is just adding the lengths of all the intervals, right? Or in other words, this is a telescopic sum. And all the terms are gonna cancel except the first and the last. And the first and the last are xn and x0. And xn and x0 are b and a. So this is the sum of the lengths of the intervals. So this quantity over here happens to be b minus a. And we are done, because then what we get is that this u, the upper sum with respect to the partition p epsilon minus the lower sum with respect to the partition p epsilon is less than epsilon over b minus a times b minus a. Now you see why I wanted epsilon over b minus a, right? This is exactly why you realize, oh, I need epsilon over b minus a. So I want this to cancel and us to get epsilon. And then that's the end of my proof. All right? Okay, so good. So now we can do a few examples. And let's this is now example 7.3.1. Let's actually integrate some functions, see how we can do it. Example 7.3.1. So here is a function, it's a very simple function. F of x is going to be 1 for x that is not equal to 1, and 0 for 1. Right? What kind of function is this? Let's draw it over here. So here are the axes. And the value at 1 is 0. And everywhere else is 1. So it's the constant 1. It has a little hole here. Right? It has a little hole at 1. Very simple function, right? It's almost constant with a little hole. So the question is this function integrable between 0 and 2? So it has a discontinuity, right? So we don't know. We cannot apply the previous theorem because it has a little discontinuity here. So is f integrable on 0 to? Who knows? Well, it's actually easy to do it. So we can just come up with a partition that will make this happen, right? If we make a partition so that the upper sum minus the lower sum becomes less than epsilon, then we know it's integrable, okay? So how do we do it? Well, here's a possible partition. So let epsilon greater than 0 and consider this partition. It will be very simple. It's only going to have 4 elements: 0, 1 minus epsilon over 2, 1 plus epsilon over 2, and 2. I'm going to assume that epsilon is tiny, smaller than 2. So this makes sense. Okay? So what is it that I'm doing? Let me put the partition right here in our picture. So one of them is 0. The other one is a little bit to the left of 1. And the other is a little bit to the right of 1. So we're like sandwiching where the problem is, right? The problem is at 1. And then 2. So we have 0. This guy over here is 1 minus epsilon over 2. This guy is 1 plus epsilon over 2 and 2. And this little interval around 1 has length epsilon, tiny, right? Okay, now let's calculate the L and the U, right? What is the lower sum? What is the lower sum? The lower sum would be, let's see, the infimum of the function between 0 and 1 minus epsilon over 2, right? So how do I write this? So what is the infimum of the function from here to here, right? Well, from here to here, the function is constant, right? It's always equal 1. So between 0 and 1 minus epsilon over 2, the function is 1 all the time. So the infimum and the supremum, both of them are 1. Maybe I'll do both of these at the same time. So this will be 1. It's 1 for both the infimum and the supremum. And what's the length of the interval? This minus that. So it's 1 minus epsilon over 2. Good. Then we have between 1 minus epsilon over 2 and 1 plus epsilon over 2, right? Now, what is the infimum in that one? Well, the infimum, see, we have this point that is 0, and all the others are 1. So the infimum is 0, right? So it's 0 times epsilon. And then between 1 plus epsilon over 2 and 2, the infimum is again 1. So 1 times 2 minus 1 plus epsilon over 2. And for the supremum, between here and here is 1, because we have points around where the value is 1. So this one will be 1. And over here, it will be 1 again. Okay, now what do we get here? Well, this is 1 minus epsilon over 2. This is 1 minus epsilon over 2 again. This is 2 minus epsilon. That's the value of the L. And for the F, we have 1 minus epsilon over 2 plus epsilon plus 1 minus epsilon over 2. So the epsilons go away, and this one is 2. Right? And we are done because the U minus the F will be equal to epsilon. Right? So we could find a partition as small as we wanted. Right? It's epsilon. You can make it as small as you want. Therefore, the function is integrable, right? And the integral is actually equal to 2, because that's what's going to be the, you can either do, well, I'm not going to do that part right now, but you can continue and show that the integral is actually 2. So it didn't really matter that we had this one discontinuity. And that's exactly what this next theorem will be about. So we're going to show that if we have one discontinuity, then there's no problem. We can still integrate it, right? And once you know you can do it with 1, well, you can do inductively that 2 is okay. 2 discontinuities will be fine. And if 2 are fine, then 3 are fine. And then a finite number of discontinuities will be okay. We can still integrate a function if it has a finite number of discontinuities. So we're going to do that. But before, I'm going to show you another one where actually a non-example. So this is going to be a non-example. So I'm going a little bit on a different order here. So I want to do this example 7.3.3. And this is our old friend, our Dirichlet function, right? So you may remember it. This is 1 if x is rational, and 0 if x is not rational. This one is difficult to draw because it has a lot of points right here at 1, all the rational numbers, and that's dense. But also a lot of points at 0 because those are the irrational numbers, which are also dense, and there's even more of them, right? So this is 1 and this is 0. So that's a poor representation that I can make of this graph. It's essentially, a cluster of, well, not really a cluster. I mean, all of these points are dense, but they are, in between any two rationals, you can find another one. In between any two irrationals, you can find another one. But there are no little intervals, right? Okay, so let's say we wanted to integrate this from 0 to 1. So is G integrable from 0 on 0, 1? So between 0 and 1 over here. Well, how would we do it? How would we do it? Well, we would calculate the upper and the lower sums, right? So what would be the upper sum and what would be the lower sum? So let's do it. So what would be, so pick a partition of 0, 1. Let P be an arbitrary partition of 0, 1. And let's calculate both of them. What would be the L? Well, the L would be, we add up the infimums of the function over xk minus 1 from 1 to n. Good. Now, what is the infimum? Let's think about it. So we divided this into some way, right? And maybe make a little larger picture here. Here. So there's 0, and there's 1, and we have some partition here. Don't exactly know how, right? But it doesn't matter. So pick one of these intervals from xk to xk minus 1. So let's say this one. And in between these two, what is the infimum of the function? Well, over here, you're going to have a bunch of points that are 0, right? And some of them that are 1. So what is the infimum going to be? The infimum will be 0, right? The infimum will be equal to the minimum in this case, and it will be 0 because you're going to have a bunch of numbers that are 0. So mk will be 0. So this is 0 no matter which interval you get. So 0 times anything means that the lower sum is always 0. The lower sum is always 0. What about the upper sum? Well, for the upper sum, now we have the supremum of the function. So we evaluate the function, but when we evaluate between xk minus 1 and xk, there will be some points that are rational, and for those we're going to get 1. So the supremum will be 1. Yes? So this will be 1, no matter which interval you get. So this is now the sum of xk minus 1. So in other words, add up the lengths of all the intervals. So this is 1. Yeah? So this, no matter what partition, you realize that? It doesn't matter which partition you pick. This is always 0 and this is always 1. Yes? So they're never the same. They will never be the same. If you then, so because these are always 0, then that means the lower interval is 0. And because these are always 1, it means the upper interval is always 1. So these two are never the same, right? These two are not the same, therefore the function is not integrable. Because L of f is different from U of f, it follows that G is not integrable. Somehow change it to f at some point. Sorry for that. This should be G. We're working with G. G is not integrable on 0, 1. And notice that it's not integrable no matter what other interval you pick, right? If you change the interval 0 to 1 to any other interval, the procedure will be the same. This one will still be 0 no matter what. And the other one will be the length of the interval no matter what. And the length of the interval is never 0, right? So Jason is asking, can I explain why the MK is 1. Capital MK is 1 little mk is 0. And yes, I can certainly explain. So let's take a look at, so let me do a bigger picture here. So here's 0 and here's 1. And here's how our function looks. It has a bunch of zeros, right? So a bunch of zeros here because those are the points that are irrational, but also a bunch of ones because those are the points that are rational, right? So if you pick any interval here, from xk minus 1 to xk, and you look at the value of a function, the g, you have some points that are 0, and you have some points that are 1, right? So the little mk is the infimum of g of x for the x's that are in xk minus 1 xk. And this set has zeros and ones, right? So what is the infimum of a collection of zeros and ones? Has to be 0, right? And capital MK is the supremum. So now you have, you want to have an upper bound. And the same thing again, when you apply the function g, you have a bunch of zeros and also a bunch of ones. So what's going to be the largest, the least upper bound? Well, it will be, the supremum in this case will be equal to the maximum, and it will be equal to 1. All right? Excellent. Good. I'm glad you understand it now, Jason, right? So that's the key with this example. So the infimum is always 0, the supremum is always 1. So when you try to do the lower sum, you're going to get 0 all the time. When you try to do the upper sum, you're going to get the length of the interval all the time. In this case, it's 1, but it could be different if I pick a different domain. And but the length of the interval is never 0. So this function is not integrable no matter what interval you pick. It never works, all right? So this function is not integrable. And this maybe suggests to you that what's happening is that if you have an infinite number of discontinuities, then it's not integrable. And that's not true. Okay, so the problem here is that this one has no continuity at all, right? This function over here is discontinuous everywhere, right? It's totally broken. But we're gonna see, I think it's an example, an exercise on the next section that our friend, the Tomae function, you may remember that one. It was also complicated like this one, the Tomae function. That one is actually integrable, even though it also has infinitely many discontinuities. But for that one, you can actually integrate it. It's not an issue, all right? By the way, this function, this Dirichlet function, is actually can be integrated if you use the other integral, the one that Lebesgue created. If you use Lebesgue integral instead of Riemann integral, then you can integrate this one, okay? Just to let you know that there are little minor differences. It's not relevant for this class, it's just a comment for future reference and general culture. Okay, so let's go back to the other theorem that I wanted to talk to you about. So this will be theorem 7.3.2. And let's put it on the book, actually. That way we read the statement with precision, and then we'll prove it. So let's go to 7.3.2 right here. It says the following. I'm going to box it so that we can all see the same thing. Yeah, this one over here. It says, if we have a function that is bounded and it is integrable from C to B. So it's bounded on AB and it's integrable from C to B for any C except A, right? So any C in between. If that happens, then it's also going to be integrable in the entire big interval. okay? So in other words, this tells you that if you have something in particular, if you have something that is continuous except at the endpoint, then it will be integral, right? Because if it's continuous, then that means it's going to be integrable if you pick any closed interval in between. So that's our assumption. So it is integrable from C to B, and we want to prove for any C, and we want to show that it is integrable on A to B. Okay, it's a kind of like a simple theorem, but it's going to help us show the part about having finitely many discontinuities and still being integrated. Okay, so let's do the proof of this. So remember, we're assuming, so let AB be an interval, a closed interval, and C some number in between. Assume F is integrable for all C. Integrable, and what interval I should say, right? Integrable on CB for all C in AB. That's our assumption. All right. And then what we want to do is we want to show that it's integrable in the big one. So how are we going to do it? Well, we're going to show that for any partition, we can, so we're going to use our workhorse, right? We're going to show that for every epsilon, there's a partition that makes the upper sum minus the lower sum less than epsilon. So how are we going to create that one? Well, easy. So let's think about first how a general partition looks. So for an arbitrary partition P of AB, this happens. The upper sum minus the lower sum looks like this. The sum from 1 to n of the supremum minus the infimum of xk minus xk minus 1. Now, I'm going to simplify the notation a little bit. Let's call this, because I don't want to carry it around all the time, so I'm going to call it, maybe you remember this from your calculus A, I'm going to call it delta of xk. So it's the little length of the interval, all right? That way we don't carry it around all the time. Okay, and the part that I want to emphasize here is, let's separate the first term, because x0 for sure is A, right? So remember, if you have our partition from A to B, so this guy is x0 always, and then we have x1, and then x2, x3, I don't know, and then this is xn, right? So I want to separate the first term from the rest. So the first term is going to look like m1 minus little m1 times x1 minus x0, which is A. And then the rest. So from 2 to n. Okay, so here's the thing. The thing is that this part, this second sum, we can control, because that's like doing the upper and the lower sums if we only wanted to integrate from x1 to b, right? And because we already know it's integrable, see, look at the assumption here. The function is integrable for any intermediate point, to the n, in particular from x1 to b. So I can already make this be as small as I want, because the function is already integrable from x1 to b. So this part I can control. I can make it, say, smaller than epsilon over 2. So all I need to do now is see if I can control this other part, this part on the right. And this one we can also control because, well, these two cannot be too big because the function is bounded. Because the function is bounded, the supremum and the infimum are going to be bounded. So this can be controlled. And then this I can make as small as I want by picking the x1 sufficiently close to A. Does that make sense? So here we go. So now this is now the idea of how I just presented to you the idea. The idea is control the second part because the function is integrable from x1 to b. Control the first part because we can make x1 really close to a. Okay, so now let's just put it all together. So let epsilon greater than 0 be arbitrary. So first I'm going to control this m1 minus m1. So because f is bounded, then I know that f of x is smaller than m, right? So this means that when we do m1 minus little m1, well, that's smaller than for sure m1 plus m1, and either of these two is smaller than m. So this is less than or equal to m. So like I was telling you, I can control this. This is at most 2m. And once I know that this is at most 2m, I now can control x1 minus a. So pick x1, let x1 be a number such that x1 minus a, so this difference, is smaller than epsilon over 4m. Right? We make this tiny. Why epsilon over 4m? Because then when I multiply these two, m1, capital M1 minus little m1 times x1 minus a will be smaller than 2m times epsilon over 4m, and that's epsilon over 2, right? Perfect. I control this part. How do I control the other part? Well, I can control the other part because I know f is already integrable from x1 to b. So because f is integrable on the interval x1 b, then there is a partition p1, I'm going to call it, such that u of f of p1 minus L of f of p1 is less than epsilon over 2, right? I can make the difference as small as I want. So I'm picking epsilon over 2. All right. And now I'm going to create the partition for the big set. What's going to be the partition for the big set? Well, pick P1 and add A. So finally, let P be P1 and add A, right? So I had a partition. Let's make a picture here. So we had X1 and B, and this had some partition. That was P1. And then I'm adding A. So I'm adding P1 together with A. That's going to be my new partition for my new partition P. And what do we know about U of FP minus L of FP? Well, that's how we started, right? That's how we started our entire proof. If we go up, you know that we calculated that. What is U minus L? And it's exactly this. It's like separate the first part and then do the definition of U minus L, but for the smaller interval from x1 to b. So this one over here, I'll rewrite it in the bottom again, is equal to precisely capital M1 minus little m1 times x1 minus a plus the regular partition with P1 instead of P. And this part is less than epsilon over 2. And this part is less than epsilon over 2. So the one we constructed is less than epsilon. And we can do this for any epsilon. Therefore, by our integrability criterion, this one is integrable. So by the integrability criterion, yes, by integrability criterion, f is integrable on AB. And that's the end of that one. All right, beautiful. And so the idea is that we could use this one now to, well, we need another little theorem that's something that you guys are also familiar to, which is that to do the integral from one point to another, we can split it in the middle. We can do that from A to B and then from B to C. Once we have that property together with this one, we can show that a function is integrable if it has finitely many discontinuities, right? So a corollary of this theorem is that if you have a discontinuity at the endpoint, then the function is going to be integrable. Because if it's continuous inside, then it will be integrable by the first theorem we proved today. So that's a little corollary. Let me write it here. It's not specifically in the book, but corollary. If f is continuous on AB, then it is integrable on AB. Right? So it doesn't matter if it's continuous or not at the endpoints, right? Oh, by the way, let's go back to the theorem. So we did it only on the left, right? We did it if it worked everything except that on A. Well, we could do the same thing on the right. So by a symmetrical argument, we could also prove a similar theorem as theorem 7.3.2, the one we just did, where we do it on the right. So that's why here I included both the left and the right endpoint. So if you're continuous inside, then you're going to be integrable, even if you consider the big closed interval. Very nice. Okay, so now the next section has actually more material. So I want to start it with 7.4, which is a nice continuation of this. So so this is called properties of integrals. And it precisely starts with the one that I was telling you. So this one, theorem 7.4.1. It says the following: if you have a function f from the closed interval AB to the reals that is bounded, and you pick C, a point in between, then f is integrable on AB if and only if f is integrable on AC and on CB. In this case, we have that the integral from A to B is the same as the integral from A to C plus the integral from C to B, right? A property that you're all familiar with. And this just tells you that as long as these integrals, each one exists, then you can always do this. You can always divide this integral into the sum of these two other ones, right? So this, together with the previous corollary, would show you that finitely many discontinuities are fine, because what do? You take your function with its discontinuities, and you use those discontinuities to divide it in this form. And because then those discontinuities will be the endpoints inside each one of their individual intervals, then the function will be integrable in each of the little pieces. Then you use this theorem, and then it will be integrable in the bigger interval, right? I just outlined how to solve that particular exercise in your homework. So I don't want to totally give you all the details, but that's essentially it. So let's proceed to the proof of this one. So it's an if and only if statement. So first we're gonna do we're gonna assume f is integrable on AB and show that then it's integrable on these two pieces. Okay, that's actually the easiest one. So let's start with that one. First, assume f is integrable on AB. And then I'm gonna show it's integrable on these two little pieces. And as usual, I'm gonna use the integrability criterion. So I'm gonna show that there is a partition that makes this one, the upper sum and the lower sum for this one be less than epsilon, and also the upper sum and the lower sum for this one be less than epsilon. That's my goal, right? My plan. So I'm gonna pick an epsilon. So let epsilon greater than 0 be arbitrary. Okay. And then because I know f is integrable on AB, I already know there is a partition that works for AB. Then by integrability criterion, the if part, there is a partition P of AB such that the upper sum minus the lower sum is less than epsilon. All right. Now what? Well, now I'm gonna assume C belongs to the partition, and if C does not belong to the partition, then add C to the partition. So assume C belongs to the partition. Otherwise, refine P with C. If it's not there, then put it in, right? When you put it in, you make this one even smaller, and then you make this one even bigger. So this will be even smaller than epsilon. The difference will be even better than epsilon, right? Whenever you refine, you make this always better. That's what we learned yesterday as well. So by possibly adding C, we make it even better. We don't alter anything. Okay, so then let P1 be the partition, but intersected with the interval AC. So in other words, pick only the elements in the partition that are smaller than C. And P2 be the ones that are bigger than C. So pick the ones that are smaller and the ones that are bigger, right? Then obviously we have this. We have that if you want to do the upper sum over P, well, you can do first the ones that are, do it with the ones that are, so do the supremum over the little interval with the partitions of the numbers that are less than C, and then do the same with the partition of the numbers that are bigger than C. So this is the same as U of FP1 plus U of FP2. And the same for the lower sum, right? And thus, if I do this, the U minus the L of the big one, remember that that one is less than epsilon. If I now substitute this, then I can write this as U of F of P1 minus L of F of P1 plus U of F of P2 minus L of F of P2. And this is less than epsilon, right? But each one of these is positive. So this is positive because we already know that the upper sum is always bigger than the lower sum. And this is also positive. So if I have two positive numbers that are less than epsilon, then that means each one of them is less than epsilon. So hence, U of FP1 minus L of FP1 is less than epsilon, and the same for P2. So I am done, right? By the integrability criterion, I find partitions P1 of AC and P2 of CB such that these differences are less than epsilon. So by the integrability criterion, F is integrable by the integrability criterion. F is integrable on AC and BC. We did it simultaneously for the two of them. All right. So that was that's the easy case because it's like you have the big partition and you can simply, you know, divide it in the two pieces: the piece that is to the left of C and the piece to the right of C, and then that's it. Each one of those two pieces have to be the differences of the upper and lower sums have to be small. The one that is a bit more complicated is the other one. So now let's do the converse. So conversely, so second, assume F is integrable on AC and on CB. So the opposite one. Okay, so then what do I know? By the integrability criterion, I know there are partitions P1 of AC and P2 of CB such that the upper sum minus the lower sum when I use P1 is less than usually epsilon, but now I'm going to use epsilon over 2 because you already have the idea that I'm going to add them, right? So these two are less than epsilon over 2, and the one for P2, the partition P2 is also smaller than epsilon over 2. So then let P be P union P2, P1 union P2, so put them together, right? So you have a partition on the left, you have a partition on the right. And each one of these two, the upper minus the lower sum is less than epsilon over 2, the upper minus the lower sum is less than epsilon over 2. Put them together, what do you get? You get that the overall is going to be less than epsilon over 2 plus epsilon over 2. And that's what we want. So let P equals the union. This is a partition of AB, of the big interval AB. And check that. The upper sum minus the lower sum will be the same as U of F of P1 minus L of F of P1 plus U of F of P2 minus L of F of P2. And this is less than epsilon over 2 plus epsilon over 2. And that's it. This shows that the function is integrable on the bigger one. Then by the integrability criterion again, but now the only if part, F is integrable on the closed interval AB. Okay, so we showed the first part. So we proved that if it's integrable on the big one, then it's integrable on each one of the two small ones. And we also showed that if it's integrable in each of the two small ones, then it's integrable on the big interval. What we haven't done is check what the answer to the integrals are. How come the sum of the integrals will be the integral of the big one? We haven't done that part. So now let's do that part. Now, so assume, so now assume F is integrable on AC and on CB, and so on AB. And let's calculate the formulas, right? So what is what is the integral from A to B? Well, by definition is the upper sum or the lower sum, because they're the same, right? Okay, but we know that there is some partition that makes this difference as small as we want. We know there is p sub epsilon, or let me call it p, such that the upper sum minus the lower sum is less than epsilon, or any epsilon, right? We can find the p that makes this happen. So I'm going to pick an arbitrary epsilon and find the p that makes this happen. And then I'm going to try to calculate in the same way what would be the, how can I relate it to the integrals over the smaller intervals. So as usual, P1 will be P intersection. So let P1 be P intersection AC, and P2 will be P intersection CB. And then what we have is that first of all, the general integral, L of f, right? So let's remember. So then this integral, which is the same as L, well, L is less than L of fp minus epsilon, right? Because this is the supremum. Well, we could do the partition over the smaller interval, the first interval, and add then the lower sum over the second partition. And these are definitely smaller than the integral from A to C plus the integral from C to B. Because, let's recall, this guy over here is the supremum of the L's, right? So it's an upper bound. It's the supremum of the L's over all partitions. So in particular, it's an upper bound of a specific partition. The same with this one. This is an upper bound of this specific partition. Okay? So if you put these two together, what it says is that the L, the integral, put it together, what it says is that this integral is smaller than the sum of these two minus epsilon. And we're going to save this one. Okay? And then to finish the proof, we're essentially going to do the same thing, but now with maximums. Instead of using the L's, or with supremums, instead of using the infimums. So here we go. Similarly, this time I'm going to start with this one. Well, this is for sure less than the U, because, let me remind you, because this is the same as the upper integral, right? And the upper integral is the infimum of all the upper sums. So this is the lower bound over all the upper sums. And this is also a lower bound over all these upper sums. So in particular for P1 and P2. And what is this? Well, this is less than, according to the property we learned, this is less than L of fp1 plus epsilon over 2, right? Remember, these were the properties we had for P1 and P2. And the next one is the same for with epsilon over 2. So now these two together is exactly L of fp, and L of fp is less than the integral from A to B. Okay, so now let's put this together, right? So what do we have? If I subtract epsilon, this is what we have. We have that the integral from A to B is less than the integral from A to C plus the integral from C to B minus epsilon. and it's greater than the integral from A to C plus the integral from C to B. Something's wrong here. One second. This is have something is weird here. I think there's should be this should be plus. Where do I get the minus here? Let me check. This is this one. This minus. This should be plus. My bad. So at the very top right here, this one should be plus. Yeah, now it makes sense. Yes. So if you take, this is the supremum, and if you take the supremum and you subtract something, you subtract a little epsilon, then you get someone that exceeds that, right? So that's, yeah, I said it correctly, but wrote the wrong sign here. And so that plus over there makes this one a plus. And now everything makes sense because I have that this integral that I want is between the sum plus epsilon and the sum minus epsilon. And because this happens for any epsilon, right, we can make this for an arbitrary epsilon. So then the only possibility is by letting epsilon go to 0, you realize that this has to be the same as that. So letting epsilon go to 0, we conclude that the integral from A to B of f is the integral from A to C of f plus the integral from C to B of f, just like we want. All right? So that's essentially it. Okay? So let me go back to the book, and we'll show at least, I'm not going to do them today because we don't have time. I have like 4 minutes or so. But I want to show you at least the next few properties that we want to show next time. So we want right here in section 7.4, this is the one we just did. And we want to now show this theorem next time, which has all these properties that you're probably familiar when it comes to integration. So if you have two functions that are integrable, then the sum is integrable, and the integral of the sum is the sum of the integrals. Excellent. If you have a function that is integrable and you multiply it by a constant, then the new function is integrable, and you can take the constant out when you want to integrate. If you have some bounded function between little m and capital M, then the integral will be bounded between little m times b minus a and big M times b minus a. This is also kind of easy if you think about it. From that one, you also can get that if you have a function that is smaller than another one, the integral preserves that inequality. And as a consequence of that, the absolute value of f will be integrable if f is integrable, and more than that, we have this, which we can call the triangle inequality for integrals. So the absolute value of the integral of f is less than or equal than the integral of the absolute value of f. You can think of it as the triangle inequality, as I was saying. All right, so that's a summary of where we're gonna pick it up next time. So we're gonna show, we're gonna prove this theorem 7.42. And our ultimate goal, of course, is to get to show the fundamental theorem of calculus, right? Tie up this integration with the derivative, right? With how they are coming up together. Okay, so this is going to be it for today. Are there any questions before I sign off? Don't forget that you need to be you need to download your exam tomorrow, okay? I forget exactly what was the time we decided it was going to be available, but whatever I wrote. And it's 24 hours. Preferably try to upload a single file if you can. If you can't, you can do page by page or things like that. It's just harder to grade when it's fractured into several files. So if possible, if you can make it into a single file, that would be great. And Ranik is asking how many questions will there be on the exam, similar to last one. So moderate amounts. I don't intend to make it longer or harder, right? So it will be the equivalent type of exam. If you look at the sample exam number 2, the one I had from last semester, you will have approximately the same number of questions and the same type of difficulty. All the questions come from the homework. They are either directly from the homework or little modifications of homework problems. Usually I make them easier, particular cases, things like that. All right? Okay. What's the structure of a final? Justin is asking. So the final will be similar. It will be a little bit longer, and not extensively longer. So about 50% longer, but it will also be a 24-hour exam. It was supposed to be scheduled, I believe, May 12th. May 12th is the date of our final exam, and the department has asked us to keep the date at least for the beginning where the exam is available. So our final exam will be given in May 12th. Our time was 12:45, so I'll make it 1 p.m. just to be, on a nice round time. And it will be a 24-hour exam as well, right? So from the 12th to the 13th, just as we had it scheduled. Any other questions?
I had a question regarding where we find the exam. Will it be under modules, under handouts, where we download it from there? And then as far as uploading it, how do we upload it? Is it again on Canvas, or do we email it to you?
It will be on Canvas. So it's not there right now, but you're going to go to assignments on Canvas. And you're going to click on it, and it will show you the instructions that I have. And I mean, I don't have it set up yet, but maybe let's see if I can show it to you for my other class so you at least get an idea.
It's set up, Professor. It's there.
What do you mean it's there?
It's there, but it says no content, but it says due
Correct.
Friday, 11:59.
Exactly. It's there, and it says no content, but once I put it on, it will look, I'll show you how it looks. Let me see if I can, let me see.
Also, it's supposed to say due Saturday, 11:59 a.m.
Correct. Right? Yeah, I have. Yes.
It doesn't say that. It says Friday.
It doesn't say that right now. Yes, I haven't touched it yet.
Okay.
Let me show you how it will look. See, my other class has an exam today, so I've been busy, so that's why I haven't gotten to setting it up for you guys yet. But I can show you for let me show you how it looks. So you will go to assignments right here, and this is my 150B class. And then when you on assignments, if you go to the exam, well, right now it says not available because it's today. So my class has an exam at 1 p.m. So at 1 p.m. it will be available, but and it will look like this. Once you click on it, it's going to have instructions like the ones, you don't need to read them right now, but they will be similar for yours. Then it will have a link for you to download the exam. And then when you want to upload it, it will have another button over here that will say click to upload. Okay?
Perfect. That makes perfect sense. Thank you.
Yes, it will be like that. Maybe I can show, let's see, the one that has passed already for my class. Well, Yeah, I can't show it to you because I'm showing it to you right now from the point of view of the professor. So you would like to see it from the student point of view, and since the other one has passed and this one is not yet available, you cannot see it. But if you have any problem, just send me an email. Mhm. Okay, so I'll see you guys next week. Good luck on your exam and stay safe.
Thank you.